Now coming back to the point of conductor dielectric boundary condition. First lectures we have I have told you that dielectric to dielectric boundary condition. If there is a dielectric media and there is another media that is conductor, so what that will affect the equations that I have told you before and that I have derived, that I have shown the derivation, that how can we derive it and how the conditions can be changed in that kind of situation. So there is a dielectric epsilon is equal to epsilon naught epsilon r, and there is a normal component and there is a tangential component, and that is the electric field. So that is the closed path of A, B, C, D, E, A, B, C, D, A, A, B, C, D, A, del W, del H, as you can see here. In dielectric, we know epsilon is equal to epsilon naught epsilon r. That is the equation. Okay. So one is dielectric, other is other is the conductor. Okay. So now the conductor dielectric boundary condition, that is the dielectricity. So we can see here the conductor dielectric boundary condition. There is the dielectricity d1, d is a dt, and dn here there is a pillbox, as we have seen before, finding out the dielectricity. Surface del S, the height is the del H, small cylinder, small cylindrical item is there is a pillbox. Same type of derivation we will continue. Let us start with the conductor dielectric boundary condition, that how we could calculate these two things. First of all, the interface between a perfect conductor and a dielectric shown in figure that we have seen in the previous two figures. Apply the equation, the closed surface equation of EDL to the path ABCDA in the figure. Same as before. Okay. Same as before means this equation, this. Okay. The change is here is that you have just got ET del W. There is no E2T or E1T or 2T. Okay. If there is a perfect conductor and a dielectric, so we can find out the second media as 0. In which media is 0? Which media is 0? Is that the conductor or the dielectric? Here you can see the conductor is equal to 0. The conductor is equal to 0. The dielectric remains the same as before. In this condition, the conductor is equal to 0. Okay. Now, here also the same. The conductor equals to 0. The electric field of the conductor equals to 0. That means in surface, the electric field of the conductor is equal to 0. In a perfect conductor, we know in the surface, the electric field is equal to 0. So, the same equation as we have derived before, just there is no E2T and E2N, all the things are 0. Just only En del is divided by 2 and E2 Et del W. So Et del W is equal to 0, that means Et is equal to 0, that means tangential component of electric field is equal to 0. As we know, Et is equal to d divided by epsilon, so dt is also is equal to 0. And also we can find out dt is equal to epsilon naught epsilon r Et. That is many common equation. T is equal to epsilon E, and that is the equation of conductor dielectric boundary condition. If there is a conductor, so the second media, the conductor media, will be 0. As well as the boundary condition for the normal component. Same. Apply the Gauss law in the small pillbox. You can get this del S, the d2n is equal to 0, so that will be out, and del q divided by del s, that you can get, assuming the del h tends to 0, same as before. Second media is 0, so dn is equal to rho is the surface charge density. So that is the, at least you can get this. Now the same conditions, the second media will be 0. So the conductor dielectric boundary condition, we have got two statements. There will be no electric field exists inside a perfect conductor. That means E is equal to 0 inside a perfect conductor. If it is a perfect conductor, any kind of thing inside of the conductor, the electric field is equal to 0. And also the external electric field, if any, is normal to the conductor surface, as given by dn is equal to rho s. External electric field, if any, is normal to the conductor surface, as given by dn is equal to rho s. Okay, the dielectricity is equal to the surface charge density. Now the third condition, conductor free space boundary condition. This is a special case of conductor dielectric condition. In dielectricity we have used epsilon r. It can be obtained by replacing epsilon r to 1. That means that will remain and that will be equal to 1. So epsilon naught en rho s, you can get dn is equal to epsilon naught en rho s. Same as if you derive dielectric, you can find out dielectric conductor and conductor free space. In free space you have to replace epsilon naught equal to 1. Like this, this is the first condition. And as in the earlier case, dt is equal to epsilon naught epsilon r et is equal to 0. You can also find out epsilon r is equal to 1, so epsilon naught et is equal to 0. That's it. And the last of all, the conductor's free space boundary condition. Here we can see in free space epsilon is equal to epsilon naught epsilon r, and conductor is equal to 0 here. So that is the conductor and free space boundary condition. In free space conductor is 0, but we can replace epsilon r as 1. That is the condition, boundary condition of conductor free space boundary condition. That's all, my dear students, of the boundary condition of electric field in the 3 different types I have discussed you in different parts. In the next lecture I will try to give you some knowledge about the magnetic boundary condition. Till there, tuned in. Thank you very much.